In this video, I'm going to talk about applying deep autoencoders to document retrieval. There was a method developed some time ago called latent semantic analysis that amounts to applying principal components analysis to vectors of word counts extracted from documents. The codes produced by latent semantic analysis can then be used for judging similarity between documents, so they can be used for document retrieval. Obviously, if deep autoencoders work much better than PCA, we would expect to be able to extract much better codes using a deep autoencoder than using latent semantic analysis. And Russ Salakutinov and I showed that that was indeed the case. Using a big database of documents, we showed that 10 components extracted with a deep autoencoder are actually worth more than 50 components extracted with a linear method like latent semantic analysis. We also showed that if you make the code very small, having just 2 components, you can use those 2 components for visualizing documents as a point in a 2-dimensional map. And this again works much better than just extracting the first 2 principal components. To find documents that are similar to a query document, the first thing we do is convert each document into a big bag of words. In other words, we have a vector of word counts that ignores the order of the words. This clearly throws away quite a lot of information, but it also retains a lot of information about the topic of the document. We ignore words like the or over, which are called stop words, because they don't have much information about the topic. So if you look on the right, I've done the counts for various words, and they're actually the counts for the document on the left. So if you look at what words we have non-zero counts for, they're vector and count and query and reduce and bag and word. That tells you quite a lot about what the document is about. Now we could compare the word counts of the query document with the word counts of millions of other documents, but that would involve comparing quite big vectors. In fact, we used vectors of size 2000, so that would be slow. Alternatively, we could reduce each query vector to a much smaller vector that still contained most of the information about the content. So here's how we do the reduction. We take a deep autoencoder and we compress the 2000 word counts down to 10 real numbers, from which we can reconstruct the 2000 word counts, although we can't reconstruct them very well. We train the neural network to reproduce its input vector as its output vector as well as possible, and that forces it to put as much information about the input into those 10 numbers as possible. We can then compare documents using just 10 numbers. That's going to be much faster. So there's one problem with this, which is word counts aren't quite the same as pixels or real values. What we do is we divide the counts in a bag of words by the total number of non-stop words, and that converts the vector of counts into a probability vector, where the numbers add up to 1. You can think of it as the probability of getting a particular word if you picked a word at random in the document, as long as it's not a stop word. So at the output of the autoencoder, we're using a great big 2000-way softmax, and our target values are the probabilities of words when we reduce the count vector to a probability vector. There's one further trick we have to do. We treat the word counts as probabilities when we're reconstructing them, but when we're using them to activate the first hidden layer, we multiply all the weights by n, and that's because we have n different observations from that probability distribution. If we left them as probabilities, the input units would have very small activities and wouldn't provide much input to the first hidden layer. So we have this funny property that for the first restricted Boltzmann machine, the bottom-up weights are n times bigger than the top-down weights. So how well does this work? We trained using bags of 2000 words on 4000 business documents from the Reuters dataset, and these documents had been hand-labelled with about 100 different categories. We first trained a stack of restricted Boltzmann machines, and then we fine-tuned with backpropagation. using a 2000-way softmax as the output. And then we tested on a different set of 4000 documents. And to test, you pick one document to be the query, one of the test documents, and then you rank order all the other test documents by using the cosine of the angles between the 10-dimensional vectors that the autoencoder gives you. You repeat this for each of the 4000 possible test documents, and then you plot the number of documents you're going to retrieve, that is how far down that ranked list you're going to go, against the proportion that are in the same hand-labeled class as the query document. This is not a very good measure of the quality of the retrieval, but we're going to use the same measure for comparing with LSA, and so at least it's a fair comparison. So here's the accuracy of the retrieval as a function of the number of retrieved documents. And you'll see that an autoencoder that's just using a code with 10 real numbers is doing better than latent semantic analysis using 50 real numbers. And of course, it's 5 times less work per document after you've got the code. Latent semantic analysis with 10 real numbers is much worse. We can also do the same thing where we reduce to 2 real numbers, and then instead of doing retrieval, we're just going to plot all the documents in a map, but we're going to colour that 2-dimensional point that corresponds to the 2 numbers produced by PCA by the class of the document. So we took the major classes of the documents, we gave those major classes different colours, and then we used PCA on log of 1 plus the count. The point of doing that is that it suppresses counts with very big numbers, which tends to make PCA work better. This is the distribution you get, and you can see there is some separation of the classes. The green class is in one place, the red class is in a slightly different place, but the classes are very mixed up. Then we did the same thing by using a deep autoencoder to reduce the documents to 2 numbers, and again, plotting the documents in a 2-dimensional space using those 2 numbers as the coordinates. And here's what we got. It's a much better layout. It tells you much more about the structure of the dataset. You can see the different classes, and you can see that they're quite well separated. We assume that the documents in the middle are ones which didn't have many words in them, and therefore it was hard to distinguish between the classes. A visual display like this could be very useful. If, for example, you saw that one of those green dots was the accounts and earnings report from Enron, you probably wouldn't want to buy shares in a company that had a green dot nearby.